lesson, we want to see that given the vector equation of a straight line, how can we find the parametric equations that represent this vector equation or the Cartesian equations that represent the vector equation. Consider this vector equation. To do so, remember that R is the position vector of n is a position vector of a general point on the line. So if we let R to be equal to the point x, y, z, or R to be equal to xi plus yj plus zk, then equating it to this and equating components will give us, we have xi plus yj plus zk equal to 6i minus k plus lambda into this. Now, equating the I components, the j components, and the k components will give us our parametric equations. That is, we have, for this I component, we have x is equal to, we have 6, and then we have negative 5 lambda. This is the first parametric equation. We now do this one, we have y is equal to, here, the j component here is 0, so we leave it out. And then here we have the j component is 3 times lambda, which is 3 lambda. And then here we have z equal to, we have negative 1. And then here we have 2 times lambda, which is 2 lambda. So this gives us the parametric equations. For the Cartesian equations, all we need to do is to make lambda the subject of these parametric equations. So, here, making lambda the subject, we have that lambda is equal to x minus 6 all over negative 5. And here, lambda will be equal to what? Y divided by 3. And here, lambda will be equal to z plus 1 divided by 2. The reason why we are creating all of this is because lambda is equal to this, lambda is equal to this, lambda is equal to this. So all of them are equal to each other. This gives us the Cartesian equation of our plane or our vector equation. Now, in this Cartesian form, one thing you should note is that the denominator of these quantities you see here represent what? The direction ratios of the vector equation. This. And from there that means we can use this to go back as seen in the next lesson.